Hello class, this is Group 4's project of the paper Apollo, Scalable and Coordinated Scheduling for Cloud Scale Computing. This was written by the Microsoft team and the Microsoft research team, and I am Michael Machovis. The general motivation behind this product was efficient scheduling for system performance. The scheduler had to do three things. It had to be able to scale, maintain fair sharing of resources, and make high-quality scheduling decisions. So there were 6 purposes of this project. The first was to balance scalability and scheduling quality. Apollo adopted a distributed and coordinated scheduling framework to independently schedule decisions made in an optimistic and coordinated manner. The second was to achieve high-quality scheduling decisions. So Apollo would schedule each task on the server that minimized the task completion time. The third purpose was to supply individual schedulers with cluster information. Apollo introduced a lightweight hardware independent mechanism to advertise load on servers. The fourth was to cope with unexpected cluster dynamics, suboptimal estimations, and other abnormal runtime behaviors. The fifth was to drive high cluster utilization while maintaining low job latencies. So Apollo introduced an opportunistic scheduling, which creates 2 classes of tasks, regular and opportunistic tasks. And the last is to ensure no service disruption or performance regression on rollout, which is particularly important because Apollo is replacing their old scheduling program that we will look at a little later on. So we come to our first challenge, which was scale. So the reason scale is so important is that the jobs that they needed to process at Microsoft could run from gigabytes to petabytes of data, and they typically saw issue peaks at over roughly 100,000 scheduling requests per second. And they also have clusters that run up to 170,000 tasks in parallel, each containing over 20,000 servers. So the challenge here was how to make optimal scheduling decisions at full production scale. The second challenge is a heterogeneous workload. So workload is very complex. The tasks are heterogeneous in many dimensions, so tasks can run from seconds to hours. Tasks can be I/O bound or CPU bound. Tasks can require from 100 megabytes to more than 10 gigabytes of memory. Short tasks are sensitive to scheduling latency, and long I/O bound tasks are sensitive to locality. So the challenge here was make an optimal scheduling decisions for this to encompass this complex workload. And the last challenge is maximizing utilization. So the clusters hosting these jobs are quite expensive. So obviously Microsoft wanted to minimize the costs of each job. So they needed to effectively use resources and maintain the performance guarantees for the users. But the biggest challenge here was that the workloads would constantly fluctuate. And as you can see by the graph, there is a 40% drop on the concurrent jobs just over the weekends. So as an overview of the Apollo program, it is the underlying schedule framework for Microsoft's distributed computation platform. So it will minimize job latency while maximizing cluster utilization. It is a large-scale data processing system. It will be used by thousands of users and uses a high-level SQL-like language for job processing. So the language that they use is called Scope. So it's a SQL-like language. It's a support structured data and unstructured data, and it's augmented with user-defined processing logic. So it's user-defined classes. So the design, it to scale, Apollo adopted a distributed and coordinated architecture. Uh, they did this because they have very complex tasks. So, in order to optimize this, they needed to distribute them among many schedulers. So, there's essentially one scheduler per job, and then each of those schedulers is working independently, making high quality decisions. Now, since these are being distributed, each scheduler does not have all the information needed, which is why they needed also a coordinated architecture. So that incorporates aggregated global cluster load information. So here we see an example of this. So there's two jobs inside of the job manager, and then three process nodes here. So the job managers are making scheduling decisions independently. One scheduler per job for scalability. Now the process nodes execute tasks on behalf of the job managers, and they are sending status updates over to the resource monitor. And the resource monitor aggregates the status information that they're receiving from the process nodes and provides the cluster load information to schedulers to inform future scheduling. Uh, so the next part of the design is representing load. So Apollo introduces a new abstraction. It exposes a schedule of future resources of availability on the server. So the server load representation must be hardware independent, be lightweight, and support the heterogeneous workload. So the abstraction that is captured in this wait time matrix. So this allows to reason about future resource availability. The next part is optimizing. So to optimize performance, the scheduler needs to simultaneously consider um, many of these conflicting factors. Um, so this could be input location, network topology, wait time, initialization time, and then the machine health and probability of failure. So to achieve this, it does so with the estimation-based scheduling. So in this part, Apollo minimizes the time for estimated task completion using the following formula, where E is estimated task completion time, I is the initialization time, W is the wait time, and R is the runtime. So Apollo minimizes the task completion time here by considering relevant factors holistically. This leads us to opportunistic scheduling. So they want to maximize utilization. And this means to use the remaining capacity. Tasks only consume idle resources. That tasks can be preempted or terminated, and tasks can be upgraded. And in addition to this, they want to limit the capacity share of each job, and they would need to use random queuing. So opportunistic scheduling allows Apollo to maximize this utilization. So now we can look at how Apollo actually performs. So in this chart, we can see the job runtime in minutes of a few different schedulers. So the Microsoft architecture allowed for it to be recorded over a period of time to see the comparison between these. So at the top, we have this green bar, which is the baseline, which is basically, as I had mentioned earlier, would be the previous production scheduler. So this scheduler, as you can see from the graph, is lacking coordination and estimates. And now down here, this dotted red-orange line is the ideal scheduler with an infinite capacity. And in here, we have what is actually Apollo and the ideal scheduler using a capacity constraint. So it kind of follows that line on the graph. So it comes much closer than the baseline. Not quite up to the infinite capacity, but performing much better in a capacity constraint perspective. And the last thing that we are going to look at is if Apollo uses the resources efficiently or not. So basically, or essentially rather, if all of these methods that Apollo put into place are effective. And the opportunistic tasks increase their share of utilization on weekends, while on the weekdays it would be more regular tasks. And this graph does show that about 90% median CPU utilization under load. So this is during the week. In particular, it does not impact the regular tasks. So you can see here that the regular tasks are less than 1 second inside the queue time at the 95th percentile. So in conclusion, before I sum everything up, I just wanted to point out a few related schedulers. There's some centralized schedulers at Quincy and LSU scheduler, hierarchical schedulers, Nessos, Yarn, and Corona, and decentralized schedulers at Sparrow and Omega. They all have a similar architecture to Apollo, which is worth mentioning that those do exist already. So, in conclusion here, the Apollo is a loosely coordinated distributed architecture, and it is deployed to clusters with over 20,000 servers. Skull is a high-quality scheduling. It's one of its main pieces. It minimizes task completion time, and it is imperative that it has consistent performance for the users. And it must maximize resource utilization by use of that opportunistic scheduling that we had discussed within the 90% median CPU utilization. And that is the end of my presentation.